We're back. Eric Hyatt again with another video on oceanography. And in the next couple of videos, we're going to make the connection between the Earth and the interior processes of the Earth and life. So this is a really cool topic. In particular, hydrothermal processes on the seafloor and how they power life in the deep, completely dark ocean. It's another really interesting topic, so let's dive right in. So as part of this section on oceanography and ocean basins, now we're going to make the connection with the planet itself and life, possibly the origin of life, but certainly whole new ecosystems that we didn't know even existed prior to about the 1970s. All right, so we've talked about the discoveries and the structure of the ocean basin, how the interior parts of the Earth are connected with ocean basins, and how ocean crust forms, and all of those details. And now we're going to start looking at how the ocean basins actually affect ocean chemistry and provide a lot of the resources for whole ecosystems on the seafloor. And the first thing we're going to start with is we're going to look at how ocean crust actually breaks down and releases elements into the ocean water itself. So we spoke previously about the basalt on the ocean floor and how it forms in these volcanic eruptions on the seafloor on the mid-ocean ridges and forming pillow basalts. And so here's a great photo of pillow basalts on the mid-ocean ridge. So it forms blobs and tubes and weird shapes because the lava is erupting out under great pressure, but the water is holding a great deal of pressure on the lava itself, so it can't really explode, it can't really flow out. It chills all around the surface where it comes in contact with the ocean water, and the ocean water is cold, it's ice water. So 0 to about 2 degrees C, it chills very quickly and it forms these characteristic pillow structures. Just to remind you, basalt is an igneous rock that's calcium, iron, and magnesium rich, and characteristically it has a small set of minerals: calcium rich plagioclase feldspar, magnesium and iron rich and calcium rich pyroxene, and then it can have a green mineral, olivine. Beyond that, possibly a little bit of magnetite and a few other minor accessory minerals, but this is the bulk of it. If you look at the chemistry though, we've got calcium, iron, magnesium, silica, aluminum, and oxygen are the main elements that we're going to be dealing with. There's many other trace elements, as we'll see shortly, that contribute to some interesting deposits on the seafloor. Things like copper, gold, platinum, and nickel, and other elements like that, which are hugely important economically. So this is a messy process. Underwater volcanic eruptions on the mid-ocean ridges produce glassy and broken textures on the seafloor. This is absolutely great for alteration to occur. So seawater can get in there and start breaking down the material, and a lot of it's not even mineralized, it's glass. And glass breaks down much easier than the crystalline form of the same material. So here's basalt erupting on the seafloor near Fiji and the Samoa, American Samoa Islands. 1,000 to 1,500 degrees C lava erupting on the surface. That's a very angry chemical reaction that's occurring at 1,000 degrees plus with freezing seawater. So the product of these volcanic eruptions and these violent volcanic eruptions is glassy, fractured material forming these pillow structures, and sometimes the lava runs out of them and forms like this hollow tube here where the lava is actually rolled right out of the pillow and chilled on the seafloor. But you see all the fractures and the rough surfaces. This provides lots of reactive surfaces for chemistry to start. And to show you the effect of what this would look like after a little bit of time, something like 20 million years or so, I want to show you this example in New Zealand. This is on the South Island of New Zealand along the eastern coast, and I was leading a field trip of students from the University of Canterbury We're looking at some of these ancient volcanic eruptions along the coast of the South Island of New Zealand. There's a lot of small volcanoes that erupted onto the seafloor about 20 million years ago, 25 million years ago. And so we hiked down, and you can actually see the roughness on the seabed there. And a lot of that is actually from lava flows. And so you look here, this whole area of what was the seafloor that's been uplifted, these are all volcanic lava flows. We had some interesting company, some New Zealand fur seals hanging out just watching us. They thought we were kind of crazy. So here's down all along the beach there, the exposure, and you can see cross sections of pillows. So here's some rock hammers for scale. That's about, 15, 16 inches long. And you see the cross sections of the pillow structures, and then the tan material filling in around them is actually limestone. But at the time, it was calcareous, skeletal shells, debris from the seafloor that settled in around those pillows. It's marking empty space originally. So this had a lot of open, empty space at one time, and then the shell material kind of settled in and filled up the spaces. But you see an interesting kind of a concentric pattern there in the cross-section of the pillows. If we look at that a little bit closer, you can see calcium carbonate, calcite, lining some of these little fractures. So this was very fractured. This is the most crystalline basalt in the middle, and then they're rimmed with what's left of glass. Here's the edge of one of those pillow basalts. The glassy rim is actually broken. This was all volcanic glass, and it broke as this was compressed. There was probably gas and other material in here, and there was some empty space inside that rim of glass. A little bit of the lava moved out along the pillow and left a cavity, and then that crunched and became compressed and broken. And you can see the calcium carbonate, the calcite here. Some of the basalt in better shape than other parts, so you see the nice black colors. That's less altered, but the rusty and even a little bit greenish, that's very characteristic of the basalt breaking down. And so the iron is oxidizing. Much of that's recent near the surface, but the greenish color is the breakdown of pyroxene, but also plagioclase, and it's making clay minerals, and the clay minerals are often green. If we look up a close-up of the rim, the glass has actually altered and it's turning all kinds of green. There's all kinds of clay minerals and alteration minerals in here as the glass has broken down. You can see the graininess near my fingertip there of the basalt, where what's left of plagioclase feldspar crystals are kind of left, and they're kind of breaking down and becoming chalky. But it's a mess. It's undergoing a lot of alteration, and much of this alteration happened early on after the volcanic eruption, when the material was still hot. The seawater was coming in there, and ions were exchanging, and the basalt was breaking down, the minerals were breaking down right there on the seafloor. Compare this to a fresh piece of basalt. This is a piece I showed you earlier from Antarctica, a piece that I collected, and here's a bubbly, glassy piece next to it. This is fresh basalt. Here's one of these fractures coming down, filled with minerals, alteration minerals like calcite, and here's the edge. There's the limestone. Here's a brachiopod, a shell, fossil shells right in here. Lots of green clay forming. That's the alteration product. And you can see all these places where seawater could get into the basalt, into the pillow. So we know from the last section when we were studying ocean basins and the ocean crust, that ocean crust is quite thin, relatively speaking, less than 10 kilometers thick at the thickest. In a lot of places, especially around the mid-ocean ridges, where the hydrothermal alteration occurs and where you have this 1500 degree heat source near the surface, that crust is much thinner, and now you've seen some of the details. There's a lot of fractures, a lot of glassy texture, a lot of opportunity for seawater to get down into the crust. So let's look at the result. The result is we've got a fractured crust with an extreme heat source below. Those are elements we need. Now we have the fractures to produce the pipes. That's our plumbing system. we have produced an amazing geothermal, hydrothermal circulation system on the mid-ocean ridges. And that's exactly what occurs. If you remember the story when we looked at exploration and scientific discoveries on the mid-ocean ridges, one of the key characteristics was that the volcanic rock seemed too cold. So there was essentially missing heat on this volcano that is the mid-ocean ridge, and Bob Ballard went and started looking for the missing heat on the seafloor. Why is the crust too cold? And lo and behold, they found that it's water cooled. Remember that part of the story. A cross section through the mid-ocean ridge where you have cold seawater that's 0 degrees or maybe as warm as 2 degrees C, just above freezing, seeping into the fractures. It gets heated up in the fractured ocean crust above the asthenosphere. It rises then, and so now we have hot water coming out of fractures, other fractures, circulating. It's a little bit like a geyser, like Old Faithful. If you took Old Faithful and instead of air pressure and you let water seep down through fractures and crevices and get heated up by a magma source, the Yellowstone intrusive magma that's below the surface in the continental crust, but only about 12 kilometers down, it heats up the water and the water comes shooting back up, but there's no water pressure like on the deep ocean to hold it down. It's just air pressure, so it heats up and starts boiling and shoots out as a geyser. There's so much water pressure in the deep ocean on the mid-ocean ridge at 2 to 3 kilometers down that the water cannot boil, and so it just rises as superheated water, like 600 degrees Fahrenheit or 350 degrees C or higher. It doesn't boil, but it circulates vigorously out of the crust. So the mid-ocean ridges are water cooled, just like the radiator in your car is cooling your car engine. The water circulating through the mid-ocean ridges in these plumbing systems is cooling the mid-ocean ridges. So we have a lot of circulation through the mid-ocean ridges in these fracture systems. Water, cold water again, seeping down through the crust and the fractures and all the cracks and crevices, heating up and then rising again, especially in the axial valley and any of the thinner parts of the crust, and coming up and venting as warm and hot water out of the crust. And the term flux refers to the volume over some amount of time, like gallons per minute or something like that, liters per hour. On a global scale, the flux through the mid-ocean ridge systems, through these hydrothermal circulation systems, is massive. We think the total volumes of the global oceans flows through these hydrothermal vent systems on the mid-ocean ridges every 3 to 10 million years. So you're exchanging the whole oceans through the mid-ocean ridges every few million years. That's pretty amazing. So as a result of these hydrothermal systems, we have brine, that is seawater, going down through all the fractures in the basalt, the glassy basalt, broken, fractured, and getting heated up. That brine is sodium and chloride and calcium rich and has all these elements in it. It heats up. It does a lot of chemical work at 1,000 degrees. A brine at 1,000 degrees that's still liquid can do a lot of chemistry. And that's exactly what happens. The seawater starts to exchange elements with the basalt and you make new minerals. And on a very simple case, it starts to exchange minerals like sodium for calcium. And so calcium starts coming out of the calcium-rich plagioclase and the calcium-rich pyroxene, and sodium goes in and exchanges. So you have new minerals forming. So if you look at a texture of a very, very altered basalt, and in this case, this is an ancient basalt that's almost a couple billion years old from Australia. It's in relatively good shape for a basalt that's been around for 2 billion years, but it's a mess. So here's a microscope slide view. We call that a thin section in geology. and this guy is a few millimeters across. We're looking through the basalt. You can see the blade shape, the elongate rectangular shapes of the calcium-rich plagioclase feldspar, or what's left of it, and you see these patches that are not transmitting light. That's hematite. And then you see all the grungy, rusty, nondescript areas. That's mostly areas where pyroxene was before. So this is just light coming through the microscope slide. Now, if we cross the polars on the microscope so that no light should come through this, we're looking at light polarized in one direction from below, and then we put a polarizer oriented 90 degrees to it above that, above the sample, and now no light should come through those except light that's twisted by crystal structures. And so now that same view, really you can see the bright gray areas are what's left of the calcium-rich plagioclase feldspar. We call those laths, or rectangular shapes. And you can actually make out a little bit what was probably some of the striations or the twinning in the feldspar. It's a little bit left, although there's virtually no feldspar left. This is all replaced by clay minerals. The dark areas, the black areas, are mostly hematite, and that's iron oxide, and it doesn't let the light flow through very well unless it's a real crystal, and then it is blood red, and that's where it got its name. Hematite, like hemoglobin, is bright blood red. And so there's actually a crystal of hematite that's letting light through. Other reactions besides the ions exchanging, you get hydration. So now we have water introduced into basalt, which was basically anhydrous. There's very little water in the basalt originally, and now we're introducing huge volumes of water. And so some of the elements, some of the compounds start to hydrate. So we have hydration reactions. So we take pyroxene, iron, magnesium, calcium-rich, could be aluminum in there too, with water, and we make a magnesium-rich clay mineral. And a common one is chlorite, and chlorite is a kind of a greenish clay mineral. So we release calcium in that reaction. So we take pyroxene with calcium magnesium, it's got iron. We make a magnesium-rich clay mineral. So we're taking magnesium from seawater. If you think back, there's a lot of magnesium in seawater, almost 1,300 parts per million. It's one of the major elements in seawater, and we're exchanging calcium. So calcium is coming out into the hot water that's flowing out of the hydrothermal system. So we're also releasing silica, and in the form of silicic acid. This is the soluble form of silica, and that goes into seawater. But if you think back to the chemistry of seawater, the silica concentration is essentially zero overall in seawater. So this is the interesting part of the story. Here's a closer view of that same basalt that we just looked at. This is more magnified, and here on the left is the view with the light going right through the microscope slide, or a thin section. Here are the plagioclase feldspar crystals that look like they've been chewed on by termites or something. They look kind of beaten up and chewed up. And they are being chewed up because they're being replaced by clay minerals. And the clay minerals are actually eating away at the feldspar and taking away the calcium, the aluminum, and the silica to make the clay minerals themselves. So here are those lath-shaped crystals, and here's this kind of greenish, brownish mess right here. This was pyroxene, or augite, and now it's completely replaced by a clay mineral, and a magnesium-rich clay mineral that's kind of greenish in color. You can also see the hematite, so big crystals of hematite blocking out the light. You can see a little bit of light transmitting here, and it looks like that blood red color that I told you about earlier. And on the right, you can see the exact same view, but now with cross-polarized light. So no light should go through except light that's going through crystals and being twisted a little bit to allow it to come through up through the microscope. And so now you can see the bright silver gray clay that's replaced the calcium-rich plagioclase feldspar, and there's a little bit of material left here. This could be calcium-rich plagioclase feldspar, but I think it's actually probably quartz that's come in here and replaced that and filled in that space. And now you can see this dark area, this big dark patch, is where the chlorite or the clay is. And it's so finely crystalline, it doesn't let enough of the light through, so it looks dark. Not completely black, but it's dark. In the transmitted view, with light just coming through the thin section or microscope slide, it just looks grungy and greenish brownish. And over here, not much light is coming through. You can see the hematite, and now you see little crystals that are letting light go through of hematite and giving that very distinctive blood red color. So a lot of chemistry has happened here. So we've had sodium-rich water come in and replace the calcium of the plagioclase feldspar, and it started to make clay because the aluminum is so insoluble. It stays as a solid, as clay, and the pyroxene has become hydrated. Magnesium actually has been added to the system. The aluminum, whatever aluminum was in the pyroxene, has stayed put, and now we've made a clay mineral. So you can see all kinds of chemistry going on. Iron has come out of the pyroxene and it's gone into hematite, iron oxide. So there's oxygen in the seawater, obviously, and now it's oxidized and forming an iron oxide in this altered mess that was basalt. So chlorite is a little clay mineral, microscopic little plates like micas. It's a very common alteration product in basalt because of the minerals that were there to start with. Add a little bit of magnesium from seawater and you get chloride all over the place. Let's take a look at the chemical exchanges and the chemistry that's changing the seawater that's going into the hydrothermal vent systems and what's coming out of the outflow of the hydrothermal vents. So seawater comes in, it's very sodium rich with 11,000 parts per million sodium, but look what's coming out of the hydrothermal flow, 10,000. So we've cut down by 1,000 ppm. So we've absorbed some of the sodium, it's gone into alteration of the feldspar mostly, exchanging for the calcium. Magnesium is one of the major elements in seawater at almost 13,000 parts per million. It's coming out as 0. So these alteration reactions are like a magnesium sponge. Sulfur is one of the most interesting parts of the story. So sulfur in seawater, as we learned before, it's almost 3,000 parts per million, but as sulfate, an oxidized form, SO4 minus 2. Very important in seawater, very important component, but it's going into the basaltic crust, heating up and reacting with all these chemical reactions, and there's electron transfer occurring, and so electrons are being transferred to the sulfur atom, and it comes out as -2. It comes out as hydrogen sulfide. It would smell like rotten eggs. And then calcium goes in at 400 parts per million, 410, and it's coming out at 800 parts per million, 860 parts per million. So the calcium is doubling. Where's the calcium coming from? Plagioclase feldspar. So sodium's going in, calcium's coming out, and pyroxene. So that augite. Calcium is coming out, magnesium is going in and exchanging to make chlorite, that clay. I put a couple other elements that are interesting on here. Silica is another interesting element. It's essentially 0 in the oceans. Some places it's a few parts per million. Other places it's very undersaturated. It's almost like a negative concentration of silica. But I put a few parts per million on there, but it's coming out at 600 parts per million as silicic acid delivered to the oceans. Now that will precipitate very quickly as the temperature drops, and it'll come down to something like 20 parts per million when the water gets cold, but the hydrothermal vents are introducing a lot of silica to the world's oceans. Iron, we talked about iron before and how insoluble it is as an oxide in the oxidized form, but in the reduced form, iron plus 2, you can put about 200 parts per million into seawater, and seawater will dissolve about that much and carry that much iron. It's coming out at 100 parts per million out of the hydrothermal vent flow. It's going in at 0.06 parts per billion or 60 parts per trillion, and it's coming out of the vent flow at 100 parts per million. So that's being introduced to the global oceans. Just to summarize a few of these elements, the result of the hydrothermal alteration that's occurring on the mid-ocean ridges, essentially all the magnesium that's being fed into the ocean by rivers is being consumed at alteration of the basalt at mid-ocean ridges. So it's a huge mass transfer of the element magnesium into the ocean crust. About half of all the calcium in the oceans comes from alteration of the basalt on the seafloor, and about all the potassium that's supplied by rivers, the global rivers of the world, to the oceans is being consumed by seafloor basalt alteration. So it's a huge sink for potassium. Geologists recognize that the mid-ocean ridges were made out of a volcanic rock and fairly fresh volcanic rock. And so one of the things they were doing was measuring the heat flux to determine how deep the magma source was to the surface. The solid basalt of the mid-ocean ridges was actually anomalously cool. And I showed you some plots of all the mid-ocean ridges from around the world, and they all had this signature of essentially missing heat. So the ridges themselves were cooler than they should have been. And when you get away from the ridges, the temperature, the heat flux was normal, exactly what people predicted. This search for the heat, the missing heat of the mid-ocean ridges, and Bob Ballard led a mission to explore the mid-ocean ridge in the Pacific called the East Pacific Rise, and they used Alvin, the submersible, to go down and actually kind of look for the missing heat on the mid-ocean ridges. And when they reached the seafloor on the mid-ocean ridge, they found these weird structures that looked like they were emitting black smoke, very thick, dark, completely black material coming out of what kind of looked like pipes on the seafloor, like chimneys almost. And they called them black smokers. This is the first type of hydrothermal vent that we're going to talk about. They're the ones that form at the highest temperature. And at greater than 350 degrees C, minerals like pyrite, iron sulfide, and iron copper sulfide, or chalcopyrite, and lead sulfide, like galena, are soluble, but when they hit the water, the cold seawater, they start to precipitate. And that makes the black color, because the true color of all those minerals is black. And they're just making little particles of sulfide minerals which look really black. So the first category, the black smokers, are where you have temperatures high enough to dissolve sulfide minerals in seawater, and then they precipitate at the surface, which makes the black color or black smoke. Sometimes you see black smokers at the surface of the earth, but that's a different thing, but very ironic. This is the type of black smoker they actually found on the seafloor. It looks like a very irregular, knobby, distorted chimney with black smoke coming out of the top. And again, the black smoke are just little particles of sulfide minerals like pyrite. But a very otherworldly kind of picture that they found. Absolutely fascinating discovery. So there's all kinds of different sizes and shapes, sometimes just coming out of fractures on the seafloor on the mid-ocean ridge. But eventually what happens is the minerals precipitate, forming the chimney. The sulfide minerals precipitate and form these pipes or chimneys. And so if you actually look at the chimney itself, it's metal. It's pyrite, it's galena, it's zinc sulfide, all these weird minerals forming the actual chimney itself. So the black color are the minerals, the sulfides, and the number one mineral is pyrite, just iron sulfide. There's chalcopyrite, which is iron copper sulfide, sphalerite, zinc sulfide, and minerals like galena, which is lead sulfide. Many economic minerals are found in these hydrothermal vent systems. Many metal economic deposits are actually ancient hydrothermal systems. We didn't really understand what they were or how they formed originally, but now we do, since the late 1970s at least. but those type of deposits form sulfide metal deposits, and those can be very rich in terms of the elements that we use in everyday life, but they also have some drawbacks, because when you take the sulfur, the sulfide, and react it with oxygen and water, one of the products that you make is rust, that iron hydroxide in that reaction, but also another product of that reaction is sulfuric acid, like the same acid that's in your car battery. That makes these type of metal deposits environmentally dangerous, costly, because if you add rainwater and oxygen to the sulfide mineral like pyrite, you end up with rust and sulfuric acid. And the sulfuric acid, but the acidity can result in the water carrying metal ions dissolved in the water, which can go into rivers and streams and drinking water and little issues like that. As a result, this type of material that comes off of these type of deposits and from mines is called acid mine drainage, and you maybe heard that term before. It's fairly controversial. These type of deposits require a lot of extra care in terms of environmental regulations and controls. So the sulfide minerals precipitate in fractures, and they build upward, and they form the pipes or chimneys, and the outflow is hydrogen sulfide rich. So that's the reduced form of sulfur. Sulfur with a -2 charge. It's been charged up with electrons in the alteration reactions at high temperature, and now that hydrogen sulfide is introduced into the oceans, which can be used as, you'll see in a little bit, as an energy source for life. Most black smokers are found on the Midocean ridge, often in the axial valleys, or within 200 meters of the Midocean ridge itself, so very close to the heat source. They form in systems like this. So the cold seawater, the cold brine that is seawater, enters the fractures and crevices in the basalt, gets heated up. It heats up over 1,000 degrees and interacts with the minerals and the glass of the basalt. That releases many of the elements and drives the chemical reactions, and then the metals and the hydrogen sulfide come shooting out the top, out of the vent, and hits the cold seawater and begins precipitating immediately. And the black smoke is the result of that. It's basically the minerals precipitating, and the minerals will continue to precipitate and fall out of the seawater as it cools and the solubility drops, and forming layers of metal-rich sediments all around the hydrothermal vent itself. So as the metal-rich and sulfide-rich hot hydrothermal water continues to vent up through the fractures, building the pipes and chimneys, those deposits, those structures are essentially metal sulfide deposits. So much metal will precipitate that it essentially forms a cap over the top. And the water's got to find another way out, another fracture, another vent has to open up. Because these are concentrated metal sulfide rich systems, they're very economical. The problem is they're 2 kilometers down under the ocean. Companies are starting to look at them as potential sources to mine and to extract metal-rich materials from the seafloor. So they form very high-grade metal deposits that are copper, zinc, lead, iron rich. Probably more important than the major metals that are present in these hydrothermal vent systems are the trace metals or accessory metals such as cobalt, platinum group elements like platinum and rhodium, gold, silver, nickel, molybdenum, rare earth elements. These elements are used in high-strength magnets, electronics, cell phones. It depends on things like gold, silver, cobalt, nickel, all these elements. So these are important elements that we use today. There are many ancient deposits around the world that we didn't really know how they formed before we found the modern hydrothermal vents on the seafloor. There's some large copper mines around the world that are essentially ancient seafloor hydrothermal vent systems. And in fact, there's one on the island of Cyprus. And Cyprus is an ancient word for copper. So it's basically a copper island. But what they mine there, and what they've mined for the last 2,000 plus years, is copper coming from an ancient seafloor hydrothermal vent system that was originally on the seafloor of the Mediterranean. So we have lots of these deposits around the world. The other really fascinating part of the discovery of the hydrothermal vent systems from that very first one that Bob Ballard discovered in 1977 was whole new ecosystems on the seafloor, whole new organisms not known previously. These ecosystems depend on the sulfur chemistry coming out of the hydrothermal vents. And you can see in this photo here all these weird creatures, which are basically a very strange type of worm that we didn't know existed prior to this discovery, right up against the hydrothermal outflow, the sulfide-rich hydrothermal outflow of a black smoker. This water is more than 350 degrees C or more than 650 degrees Fahrenheit flowing out of this, but yet life exists, and it exists because of the sulfur chemistry. Here's another view of some of these worms in a little bit more quiet water setting on the hydrothermal vent systems. This is all basalt, pillow basalts, and hydrothermal fluids are coming out of here. These things can be up to 6 feet long. They're called tube worms for obvious reasons. But the most important part of the ecosystem on this hydrothermal vent system is this white material on the basalt, and it's actually a bacteria. So it's colonies of chemical bacteria that's living off the sulfur chemistry. And that's going to open up a whole new world for us in terms of understanding life, and that's the next thing we're going to talk about. So in the next video, we're going to finish talking about hydrothermal vents at lower temperature this time, and then we're going to move on to making the connection with life and possibly the origin of life in these whole new ecosystems that were discovered as part of the hydrothermal vent system. It opens up a whole new understanding of chemical processes driving life on this planet. So see you then.